simulations predicted chaos. When cosmologists modeled the very first galaxies forming in the early universe, the results were consistent across virtually every simulation platform. Young, early galaxies should be irregular, chaotic, asymmetric structures. Blobs of star formation loosely organized around gravitational centers, constantly disrupted by mergers, gas inflows, and violent stellar feedback. The smooth, ordered shapes that characterize galaxies in the local universe, spirals with elegant arms, smooth ellipticals with clean light profiles, were supposed to be the product of billions of years of gravitational settling and quiet evolution. Early galaxies, by every prediction, should look like the universe's rough drafts. Webb showed something different. When astronomers began analyzing the morphologies, the structural shapes of early galaxies in Webb's images, they encountered a population dominated by a specific form: flat, elongated disks, not the rotationally symmetric spirals of mature galaxies, but thin, extended structures, like a lens or a flattened oval, with the bulk of their stellar mass arranged along a single plane. This form, sometimes called a prolate or oblate disk, depending on the specific geometry, was found in a significant fraction of early galaxies across multiple Webb survey programs. One survey found that thin disk structures made up a substantially larger share of early galaxy morphologies than any simulation had predicted. The problem with these disks is not just their existence, it is their implied history. A flat, ordered disk requires the gas that formed it to have settled into a coherent rotation pattern. Gas falling into a dark matter halo from multiple directions, as it does in simulations, produces irregular, chaotic structures. To produce a thin disk, the infalling gas must have some degree of organized angular momentum to begin with, meaning it must have been rotating in a broadly consistent direction before it ever reached the galaxy. In the standard model, the angular momentum of infalling gas at early times is expected to be disordered, coming from many directions across a chaotic young universe. The smooth disks Webb found require early universe gas to have been more ordered, more coherent in its rotational structure than the model predicts. Several explanations are under investigation. One involves the role of cosmic filaments, the thin strands of dark matter and gas that connect galaxy clusters in the large-scale cosmic web. Simulations show that gas flowing into forming galaxies along these filaments tends to carry more coherent angular momentum than gas accreted from random directions. If early galaxies were embedded in a more developed filamentary network than standard models predict, the disk morphologies might follow naturally. But this explanation requires the cosmic web itself to have been more organized at early times than lambda CDM predicts. Another piece of structure arriving ahead of schedule. There is a second morphological finding that cuts even deeper than the disks. Because among the flat, elongated structures Webb catalogued in the early universe, several showed something that had no business being there at all: spiral arms, fully developed, sweeping spiral structures, in galaxies existing at a time when the standard model says spiral formation had barely begun. And the implications of those arms reach into the deepest assumptions of how galaxies evolve. Spiral arms take time. That is not an assumption. It is a physical consequence of how disk galaxies work. A spiral arm is a density wave, a region of compressed gas and stars that sweeps through a rotating galactic disk like a slow-moving traffic jam on a circular highway. The cars keep moving through the jam, but the jam itself persists. For that wave pattern to establish itself, the disk must have been rotating long enough for the density pattern to organize, reinforce, and stabilize across the full width of the galaxy. Estimates for how long that process takes in the local universe range from several hundred million to over 1 billion years after a disk first forms. You need the disk first. Then you need it to rotate. Then the wave pattern gradually emerges from small gravitational perturbations as the disk matures. Webb found spiral structure in galaxies at distances corresponding to less than 1 billion years after the Big Bang. One confirmed example, identified in early Webb survey data, showed clear spiral features at a redshift, placing it roughly 2 to 3 billion years after the Big Bang. That was already surprising, but deeper surveys pushed the finding further back. Candidate spiral structures began appearing at redshifts corresponding to under 1 billion years of cosmic age. Some of the most extreme candidates sit at distances where the universe was younger than the minimum formation time for spiral arms, according to the standard timeline. The confirmed cases at 2 to 3 billion years are already difficult for current models to explain. At those distances, simulations predict that most disk galaxies should still be in the irregular turbulent phase that precedes spiral development. Finding ordered spiral structure That early requires either the disk formed earlier than the galaxy's observed redshift implies, or the spiral formation process ran faster than any simulation has reproduced. The deeper candidates, the ones at under 1 billion years, are currently classified as high-priority targets for spectroscopic follow-up. If confirmed, they would represent the single most structurally mature objects ever observed at those distances. The significance extends beyond the structural question. Spiral arms are not just aesthetically striking. They are engines of star formation. The density wave compresses gas as it passes through, triggering bursts of star formation along the arm. A galaxy with functioning spiral arms is a galaxy with a self-sustaining cycle of stellar birth built into its architecture. If early galaxies had functional spiral arms, they had access to an efficient self-organizing star formation mechanism far earlier than the model allows, which would help explain at least partially why they accumulated stellar mass so quickly. But it raises its own question. Spiral arms are fragile. Mergers destroy them. Violent gravitational interactions from neighboring galaxies disrupt the density wave pattern. In the early universe, where galaxy mergers were far more common than today, maintaining an ordered spiral structure should have been nearly impossible. And yet, ordered, sweeping, present, the shapes Webb is finding in the early universe keep telling the same story from different angles. Structure arrived ahead of schedule. Order appeared where chaos was predicted. Something in the earliest chapters of cosmic history ran faster, smoother, and more efficiently than the model that was supposed to describe it. And the evidence for that early efficiency is written not just in the shapes of galaxies, but in their chemistry. Inside these ancient systems, a periodic table is already filling in, element by element, and the timeline it implies is deeply unsettling. Every element heavier than helium was built inside a star. That sentence contains an entire origin story. Carbon, oxygen, nitrogen, iron, calcium, every atom that makes up the ground beneath your feet, the air in your lungs, and the cells in your body was forged inside a stellar core over millions of years, and then scattered into space when that star died. The universe started with only hydrogen, helium, and trace amounts of lithium. Everything else on the periodic table had to be manufactured, element by element, through generations of stellar birth and death. This process has a pace. Stars take millions of years to form, live, and explode. Each generation enriches the surrounding gas slightly. The next generation forms from that slightly richer gas, and so on. Astronomers call this chemical enrichment, and it accumulates slowly across cosmic time. When Webb analyzed the spectra of early galaxies, some of them showed chemical enrichment levels that required multiple stellar generations to produce, at distances corresponding to less than 1 billion years after the Big Bang. One confirmed case involved a galaxy whose spectrum showed oxygen abundance approaching levels comparable to galaxies in the local universe. Galaxies that have had over 10 billion years to enrich themselves chemically. This particular early galaxy had managed comparable enrichment in a fraction of the time. The oxygen abundance is especially diagnostic, because oxygen is produced primarily in the cores of massive stars during their lifetimes, and released in supernova explosions. The quantity of oxygen in a galaxy's interstellar gas directly reflects how many massive stars have formed, lived, and died inside it. High oxygen abundance means many generations of massive stars have already completed their life cycle. For an early galaxy to show high oxygen abundance, it must have already run through a rapid sequence of stellar generations, each one forming, burning through its fuel in millions of years, exploding, enriching the surrounding gas, and triggering the next generation. Multiple cycles, all compressed into an impossibly short window. The chemical evidence aligns with and strengthens every other line of evidence Webb has accumulated. The mass problem, the brightness problem, the structural maturity problem, all point at the same underlying reality. The early universe ran its stellar chemistry at a pace the model does not accommodate. Some researchers point to the population 3 stars discussed earlier as the accelerant. Those enormous, short-lived first-generation stars would have produced and released heavy elements on a dramatically compressed timescale compared to modern stellar populations. A generation of population 3 stars living and dying within 10 million years could have enriched surrounding gas to levels that would take billions of years to reach through normal stellar evolution. This is a plausible theoretical framework. Population 3 enrichment as the chemical head start that explains what Webb is reading in early galaxy spectra. But it requires population 3 stars to have existed in large numbers, formed quickly, and died violently, all in the first 100 million years of cosmic time. That is a dramatic claim. Plausible, supported by theory, consistent with the data, but unconfirmed by direct observation. And the chemical evidence carries one more layer of strangeness, because one of the byproducts of stellar death is something that should have been nearly absent in the early universe, something that requires destruction to create, something whose presence in early galaxies deepens the mystery by yet another degree: dust. Dust sounds mundane. In the context of the early universe, it is extraordinary. Cosmic dust is not the fine household particles you brush off a shelf. It is composed of tiny solid grains, a few millionths of an inch across, made of silicates, carbon compounds, and other heavy materials. It forms in the cooling outer layers of dying stars, and in the dense debris clouds left behind by supernovae. It absorbs ultraviolet light and re-radiates it as infrared. It is the raw material from which planets form. Without cosmic dust, there are no rocky planets, no chemistry complex enough for biology, and almost certainly no life. Here is the critical fact: dust requires heavy elements to form. You cannot build a silicate grain from hydrogen and helium. You need silicon, oxygen, carbon, iron. All of these are stellar products. All of them require generations of stars to live and die. In the early universe, dust should have been nearly absent. The first billion years of cosmic time should have been a dust-free epoch, with only the cleanest primordial gas, and whatever trace enrichment the first stellar generations had managed to produce. Webb found dust in galaxies less than 1 billion years old. Several early galaxies in Webb's survey data showed clear infrared signatures of significant dust content. One analysis identified a galaxy at roughly 700 million years after the Big Bang, containing a mass of dust equivalent to tens of millions of times the mass of our own star. A vast quantity of solid, heavy, element-rich material, already accumulated and distributed through a galaxy that had barely had time to exist. The production rate problem is severe. Forming that quantity of dust requires a corresponding quantity of heavy elements. Producing those heavy elements requires a corresponding number of stellar deaths. Each supernova produces only a fraction of that dust quantity. To accumulate the observed dust mass in under 700 million years demands a supernova rate that strains credibility under standard stellar evolution models. Some researchers have proposed that asymptotic giant branch stars, a class of evolved medium-mass stars in their final phase, could be significant dust producers in the early universe. These stars are efficient dust factories and operate on somewhat shorter timescales than previously appreciated. Including them in early universe chemical models helps close the gap partially. Others point again towards population 3 stars. Their extreme masses would have produced correspondingly extreme amounts of heavy elements in their death explosions. A generation of population 3 supernovae could have seeded the surrounding gas with enough material to explain the dust masses Webb is measuring. Neither explanation is yet confirmed as sufficient on its own. The dust problem remains an open and active research question, but it adds a third chemical constraint alongside the oxygen abundance and the evolved stellar populations. 3 independent chemical signals, all pointing at the same conclusion. The early universe ran through stellar generations rapidly, in ways that produce chemical complexity far ahead of schedule. And the weight of that evidence, chemical, structural, and mass-based, has pushed some researchers toward a question that would have seemed professionally dangerous to ask just a decade ago. What if the universe is older than we think? The age of the universe is one of the most precisely measured numbers in all of science: 13.8 billion years. Derived from multiple independent methods, the rate of cosmic expansion measured across thousands of galaxies, the temperature and pattern of the cosmic microwave background, the ages of the oldest stars in globular clusters, and the abundances of light elements produced in the Big Bang. All of these converge on the same answer within a narrow margin. It is one of the most robust results cosmology has ever produced. And yet, a small but growing number of researchers have begun asking whether that age might be wrong. Or more precisely, whether the universe as we measure it today could represent a phase of something older, and whether Webb's impossible early galaxies are pointing toward a cosmic history that began before the event we call the Big Bang. This is a minority position, firmly in theoretical territory, but it is being advanced by credentialed researchers in peer-reviewed publications, so it deserves honest examination. The argument runs as follows. The standard age measurement assumes lambda CDM correctly describes the full history of the universe from the Big Bang onward. If lambda CDM is wrong in certain details, those details could affect the inferred age. Some alternative cosmological models, particularly those that modify how dark energy behaved in the early universe, produce slightly different age estimates. A few produce significantly different ones. One proposal, advanced seriously in recent years, suggests the universe could be as old as 26.7 billion years, nearly double the standard estimate. This claim comes from a specific alternative model that interprets galaxy evolution data differently and proposes a longer cosmic history. The mainstream reaction has been skeptical. Most cosmologists consider the cosmic microwave background data alone sufficient to anchor the 13.8 billion year estimate firmly. But the proposal highlights that the age question and the early galaxy question are connected. If the universe is older than currently measured, the impossible galaxies become less impossible. They had more time. The timelines relax. The challenge is that changing the age of the universe requires explaining why the cosmic microwave background appears to indicate a younger universe. That background is the afterglow of the Big Bang itself, and its pattern and temperature encode the age of the universe at the time of emission. Changing the age requires reinterpreting that pattern, which requires modifying the physics of the early universe in ways that must remain consistent with all other observations. No alternative model has yet managed that reinterpretation without breaking something else. So the age question remains open at the theoretical edges, firmly settled at the mainstream center. What Webb has done is give the theoretical edges new and specific observational ammunition. And directly connected to the age question is a deeper one, the one researchers rarely said out loud until recently. A question about what, if anything, came before everything. Cosmology has a standard answer for the question of what came before the Big Bang. The answer is that the question may not have meaning. Time itself, according to general relativity, emerged with the Big Bang. Asking what came before is like asking what is north of the North Pole. The coordinate system breaks down before you get there. That answer has always been philosophically uncomfortable, and Webb's findings have given researchers on multiple theoretical fronts new reasons to push past it. Two major theoretical frameworks address the pre-Big Bang question, and they reach opposite conclusions about what Webb's early galaxies imply. The first is cosmic inflation, the dominant theory of the very early universe. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing by an incomprehensible factor in an incomprehensibly short time. This expansion smoothed out the early universe to the uniform state we observe in the cosmic microwave background, generated the small density fluctuations that seeded all structure, and solved several other theoretical problems that a non-inflationary Big Bang could not address. Under inflation, the Big Bang was the beginning. Nothing preceded it in any physically meaningful sense. Webb's early galaxies challenge inflation indirectly, because the density fluctuations inflation generated are supposed to define the initial conditions for all structure formation. If those initial conditions are insufficient to produce the structures Webb is observing, the inflationary parameters need revision. Some researchers are now working to determine whether modified inflationary models can produce the initial density fluctuations required to seed Webb's early structures. The second framework is cyclic cosmology. Under certain cyclic models, the Big Bang was a transition between a previous phase of the universe and the current one, a bounce, a collision between higher dimensional structures, or a phase transition in a pre-existing space-time. The universe we inhabit is one cycle in an ongoing sequence. Structures from previous cycles could theoretically influence the starting conditions of the current one, potentially providing a head start for early galaxy formation. Cyclic cosmologies remain highly speculative. There is currently no confirmed observational signature that distinguishes a cyclic universe from a standard inflationary one. Webb's early galaxy findings have been cited by proponents of cyclic models as circumstantial support, since a pre-existing cosmic heritage could explain why structure appeared so early. But circumstantial is the operative word. The claim is theoretical extrapolation, not confirmed evidence. What is confirmed is that the very earliest observable epoch of the universe, the one Webb, is now probing directly, contains surprises significant enough to force theorists on all sides to revisit their foundations. The instrument doing the probing deserves a closer look, because the reason Webb sees things Hubble never could is not just a matter of a bigger mirror, it is a matter of a completely different kind of vision. For 3 decades, the Hubble Space Telescope was humanity's deepest eye. It showed us galaxies billions of light years away. It measured the expansion of the universe with precision that reshaped cosmology. Its deep field images, taken by pointing at a seemingly empty patch of sky for days or weeks, revealed thousands of distant galaxies and became some of the most celebrated scientific images ever captured. Hubble saw primarily invisible and ultraviolet light, with some near-infrared capability added through later servicing missions. For the vast majority of cosmic history, That was sufficient. But the most distant universe, the first billion years, sits beyond Hubble's reach for a specific physical reason. The universe is expanding. As it expands, light from distant objects stretches. The further the object, the more the light stretches. For objects at the distances where the early universe lives, the light has stretched so far that it exits the visible spectrum entirely and shifts into infrared wavelengths. By the time light from a galaxy at redshift 10 reaches us, it is invisible to human eyes and to any telescope designed primarily for visible light. Hubble was built for the visible universe. The early universe speaks in infrared. That gap is absolute. No tuning of Hubble's instruments could bridge it. The early universe was simply outside Hubble's physical language. Its primary mirror spans roughly 21 feet, about 2.5 times the collecting area of Hubble's mirror. Larger mirrors collect more light, which means fainter objects become detectable. But the mirror size is almost secondary to the instrument design. Every detector on Webb is tuned specifically for infrared wavelengths. Its sunshield, a 5-layer structure the size of a tennis court, blocks heat from the Earth, Moon, and star to keep the telescope cold enough that its own thermal glow does not overwhelm the faint infrared signals it is hunting. Webb operates at roughly negative 448 degrees Fahrenheit, just 40 degrees above absolute zero. At that temperature, the telescope itself stops being a source of infrared noise. The result is a telescope that can detect infrared sources roughly 100 times fainter than anything Hubble could see in that wavelength range. 100 times. That is the difference between seeing a distant campfire and detecting the warmth of a single candle at the same distance. When Webb looked at the same patches of sky Hubble had studied for decades, it found objects Hubble had no capacity to detect. Galaxies at redshifts of 8, 10, 12, 14, and beyond appeared in Webb's data like suddenly visible stars emerging after your eyes adjust to the dark. The transition from Hubble to Webb was not an incremental improvement. It was a categorical shift in observational capability, comparable to the shift from the naked eye to the first optical telescope. A door opened into a previously invisible era of cosmic history. And through that door came every impossible galaxy discussed in this story. Not because the galaxies were new. They had been sitting there for billions of years, emitting their infrared light into space. They were impossible to see before Webb. Now they are impossible to ignore. The most chemically extreme of them, one specific galaxy whose spectral data forced a rewrite of stellar evolution timelines, illustrates just how severe the revision needs to be. It did not announce itself dramatically. It appeared in Webb's survey data as a compact, relatively bright source at an extreme redshift. Standard procedure: flag it, add it to the spectroscopic follow-up queue, wait for confirmation. When the spectroscopic data came back, the research team ran their analysis expecting the usual result. A young galaxy, modest chemical enrichment, broadly consistent with the standard model, perhaps slightly ahead of schedule. Instead, the spectrum showed oxygen and carbon abundances approaching the levels observed in galaxies in the nearby universe. Galaxies with over 10 billion years of chemical history behind them. This particular galaxy existed at a time when the universe was under 500 million years old. The chemical enrichment level required working backwards through stellar evolution models, demanded a history of intense star formation, running across multiple complete stellar generations, each cycle producing, dispersing, and reincorporating heavy elements into new stars. The minimum elapsed time for that chemical history, using the most aggressive star formation rates the models allow, pushed uncomfortably close to the age of the universe at the time of observation. Some analyses suggested the chemical history implied by the spectrum may have required more time than the galaxy had existed. That sentence deserves to sit alone for a moment. The chemical record inside the galaxy pointed to a history longer than the galaxy's confirmed age. Like reading tree rings in a sapling and counting more rings than years the tree has been alive. The research team considered instrumental effects. They checked for contamination in the spectrum. They reran the stellar population models with different input parameters. They tested whether an unusual initial mass function, a distribution of stellar masses skewed heavily toward the most massive stars, could compress the enrichment timeline sufficiently. The massive star scenario helped. Galaxies dominated by very massive, short-lived stars produce and disperse heavy elements faster than normal stellar populations. This is the population 3 connection again, suggesting that the very first stellar generations in this galaxy were dominated by extreme mass stars that lived and died in compressed timeframes. Even with that correction applied, the chemical timeline remained tight, barely consistent with the available time, and only under the most aggressive assumptions. When the team published, the paper was careful in its language. They did not claim to have found a galaxy older than the universe. They described their results as requiring either extremely efficient early star formation, dominated by very massive stars, or a revision of stellar nucleosynthesis models at low metallicity, meaning under chemically pristine conditions. Both revisions are significant. Both have implications that ripple outward through multiple areas of astrophysics. And this galaxy was not unique. It was the most extreme confirmed case in a distribution of early galaxies showing elevated chemical maturity. The distribution itself is the signal. Outliers are expected. A systematic trend toward chemical overmaturity across hundreds of early galaxies is evidence of a process that operated differently in the early universe. That process left another signature, one that does not involve chemical abundance at all, one that involves raw, blinding, ultraviolet light. Ultraviolet light is the radiation of youth. Young, massive hot stars pour ultraviolet radiation into space at rates that older, cooler stellar populations cannot match. When a galaxy is actively forming large numbers of massive young stars, it blazes in ultraviolet. When star formation slows or stops, that ultraviolet glow fades. Astronomers use ultraviolet brightness as a direct tracer of current star formation activity. The relationship between a galaxy's ultraviolet output and its star formation rate is one of the most calibrated tools in observational astronomy. It has been tested across thousands of galaxies at many different cosmic distances. The calibration holds. The relationship is reliable. Webb found early galaxies producing ultraviolet radiation at rates that the calibrated relationship says are impossible given their estimated masses. This is called the ultraviolet luminosity excess, and it is one of the most statistically robust problems Webb has delivered to cosmology. It appears across large galaxy samples. It is not driven by a handful of unusual outliers. It is a systematic offset. Early galaxies at high redshift producing more ultraviolet light than their stellar mass should allow, persisting across the full range of distances Webb has surveyed in the early universe. The magnitude of the excess in some cases reaches a factor of 10. A galaxy producing 10 times the ultraviolet output expected for its mass is not a calibration error. It is a statement that either the mass estimates are dramatically wrong, or the stars inside these galaxies are producing light in a fundamentally different way. 3 physical explanations have been seriously proposed. The first returns to population 3, and extremely massive stars. As discussed, stars with masses hundreds of times greater than typical stellar masses produce ultraviolet radiation with extraordinary efficiency. A galaxy whose stellar population is dominated by such extreme mass stars would show exactly the kind of ultraviolet excess Webb is measuring. This explanation is theoretically consistent, but awaits direct confirmation. The second involves active galactic nuclei, supermassive black holes in the process of actively feeding. An actively feeding black hole produces enormous quantities of ultraviolet and higher energy radiation from the superheated disk of infalling material around it. If a significant fraction of the early galaxies Webb observes have active central black holes, their ultraviolet output would be boosted above what stellar populations alone could produce. Webb has confirmed active galactic nuclei in several early galaxies. Whether the fraction is large enough to explain the full ultraviolet excess across the population is still being determined. The third explanation is the most structurally challenging for the standard model. It proposes that the initial mass function itself, the distribution of stellar masses that forms in any given burst of star formation, was fundamentally different in the early universe. An early universe initial mass function skewed toward very high stellar masses would naturally produce populations that generate far more ultraviolet light per unit of total mass. If the initial mass function was different early on, it means the basic rule governing how stars form changed over cosmic time. That is a significant revision to stellar physics, one that would propagate changes through essentially every area of galaxy evolution theory. The ultraviolet excess is confirmed, the cause is actively debated. And whatever the cause turns out to be, it connects directly to what was happening between galaxies in the early universe, in the spaces where galaxies were meeting, colliding, and feeding each other at a rate nobody predicted. Galaxies are not isolated islands. They interact. They pass through each other, distorting shapes and triggering star formation. They collide and merge, combining their mass into larger systems. They strip gas from each other through gravitational tides. Galaxy interactions are a fundamental driver of evolution, and their frequency determines the pace at which the universe builds larger and more massive structures. Under lambda CDM, the galaxy merger rate peaks at around 2 to 3 billion years after the Big Bang, and declines as the universe expands and galaxies spread further apart. The early universe, before that peak, is predicted to have a lower merger rate because galaxies are still forming and the large-scale structure is still assembling. Webb observed the opposite. Multiple survey programs using Webb's imaging found galaxy pairs, interacting systems, and merger candidates at rates significantly exceeding lambda CDM predictions at early cosmic times. One study examining galaxies in the first 2 billion years found a merger fraction roughly 3 to 5 times higher than the model's predictions for that era. A higher merger rate in the early universe has compounding consequences. Mergers between gas-rich galaxies trigger intense bursts of star formation. The gravitational disruption compresses gas clouds, overwhelming the thermal pressure that keeps them from collapsing, and igniting stellar nurseries across both merging systems simultaneously. A galaxy experiencing a major merger can temporarily form stars at rates 10 to 50 times its typical baseline, a phenomenon called a starburst. If early galaxies were merging more frequently than predicted, they were triggering more starbursts, more frequently across a larger fraction of the cosmic volume. This provides a natural accelerant for the rapid mass assembly Webb keeps documenting. It also affects the central black holes. Galaxy mergers drive gas toward galactic centers, feeding central black holes and triggering active galactic nucleus activity. A universe with a higher early merger rate would produce more rapidly growing black holes at early times, which connects directly back to the oversized black holes Webb has confirmed. The merger rate discrepancy is real and confirmed across multiple independent programs. The explanation within the standard model requires adjusting the initial density fluctuations to produce a more clustered early universe, meaning galaxies were more likely to find each other and interact because they were born closer together than the model predicted. This clustering adjustment, like the dark matter halo efficiency adjustment discussed earlier, requires modifying the initial conditions of the universe. The conditions immediately following the Big Bang, encoded in the cosmic microwave background, would need to have been slightly different from their measured values to produce the observed clustering. That difference is small enough that the cosmic microwave background data cannot definitively rule it out. But it is a revision, one more place where the standard model needs to bend to accommodate Webb's observations. And there is one specific early galaxy that bends the model in a direction nobody expected. Because while most early galaxies show signs of dark matter doing exactly what the model predicts, one showed almost none at all. Dark matter is supposed to be everywhere. The standard model treats dark matter as the skeleton of all cosmic structure. Every galaxy sits inside a dark matter halo. The halo predates the visible galaxy, forms faster than ordinary matter can organize itself, and provides the gravitational well into which gas eventually falls. Remove the dark matter halo, and there is no gravitational seed around which a galaxy can form. No halo means no galaxy. That is the standard picture. It is held up across virtually every observation conducted over decades. Webb found an early galaxy that appears to violate it. The galaxy, confirmed at a distance placing it in the first 2 billion years of cosmic history, showed rotation and velocity measurements inconsistent with a massive dark matter halo. When astronomers measured how the stars inside this galaxy were moving and compared those velocities to what a standard dark matter halo would predict, the numbers did not match. The stars were moving as though most of the mass inside the galaxy was the visible stellar mass alone, with far less dark matter than the model demands. In the local universe, similar dark matter-poor galaxies have been found, and they generated significant controversy. The prevailing explanation for those local cases involves tidal stripping, where a nearby massive galaxy gravitationally pulls dark matter out of a smaller companion over billions of years, depleting its dark matter halo. For an early galaxy at this redshift, the tidal stripping explanation is harder to apply. The universe at that age was not old enough for the long, slow process of tidal stripping to have depleted a full dark matter halo. The galaxy would need to have formed with very little dark matter from the beginning. That possibility challenges a fundamental assumption. If some galaxies can form and exist with minimal dark matter halos, the role of dark matter in galaxy formation is more complicated than the model assumes. Either dark matter distributes itself unevenly in the early universe, in ways current models do not capture, or some other mechanism can substitute for the gravitational anchoring dark matter is supposed to provide. Some researchers have proposed modified theories of gravity as an alternative framework. Under certain modified gravity models, ordinary visible matter produces stronger gravitational effects at low accelerations than standard gravity predicts, potentially removing the need for dark matter in some regimes. These models have had mixed success explaining other observations, and remain controversial. The early dark matter-poor galaxy is a confirmed anomaly. The explanation is actively contested, and it deepens the already substantial pressure on the standard model from a completely new direction. The behavior of dark matter itself, under early universe conditions, may have been different from current assumptions. That possibility connects to a theoretical proposal that has gained significant traction as cosmologists try to reconcile Webb's findings with the existing framework without abandoning it entirely. A proposal that adds a new ingredient to the universe's energy budget, specifically tuned to operate in its earliest chapters. Dark energy is the force driving the universe's accelerating expansion. It was discovered in the late 1990s through observations of distant supernovae, and its existence is confirmed by multiple independent measurement methods. In the Standard Model, dark energy is a constant property of empty space, a fixed energy density that does not change over time, and has been present at the same level throughout cosmic history. That constancy is an assumption, a well-motivated one, but still an assumption. Some cosmologists have proposed that dark energy was different in the early universe. Specifically, that there was an additional component of dark energy that was active only during the first million years or so of cosmic history, and then diluted away, leaving the universe with only the constant dark energy component we observe today. This hypothetical component is called early dark energy. The original motivation for early dark energy had nothing to do with Webb's galaxies. It came from a different crisis in cosmology, the Hubble tension. But early dark energy, introduced to address the Hubble tension, turns out to have interesting side effects on early galaxy formation. By modifying the energy content of the early universe, early dark energy models alter the rate at which density fluctuations grow into structure. In some versions, the modification produces faster early structure growth, which would allow dark matter halos to build mass more quickly, giving galaxies a head start on assembly. This makes early dark energy a candidate solution for multiple Webb-related problems simultaneously. It could, in principle, explain the accelerated galaxy formation, the early cluster, the oversized black holes, and the ultraviolet luminosity excess, all within the existing mathematical framework of cosmology, by adjusting the energy content of the early universe, rather than revising galaxy formation physics directly. The proposal is compelling as a unifying explanation. It is also, currently, unconfirmed. Observational constraints on early dark energy are significant. The model must remain consistent with the cosmic microwave background, with nucleosynthesis, and with the large-scale structure of the intermediate distance universe. Several versions of early dark energy have been ruled out or severely constrained by these tests. The versions that survive are narrow and require careful parameter tuning. Webb itself is contributing to the early dark energy tests. By measuring the galaxy population across a range of early universe epochs with high statistical precision, Webb is providing the observational data against which early dark energy predictions can be checked. Some versions of the model make specific, testable predictions about galaxy abundance and properties that Webb is now in a position to verify or falsify. The tension between the Standard Model and Webb's observations does not exist in isolation. It connects to other cracks in the cosmological framework that were already there before Webb launched. And the deepest of those cracks runs through the measurement of the universe's expansion rate itself. There are two ways to measure how fast the universe is expanding. The first looks backward. Astronomers analyze the cosmic microwave background, the ancient light released 380,000 years after the Big Bang, and use the pattern of temperature fluctuations embedded in it to calculate the expansion rate of the universe. This method anchors itself firmly in the early universe. It produces a precise number. The second looks around. Astronomers measure the distances to nearby galaxies using standard candles, objects with known intrinsic brightness, and compare those distances to the galaxy's recession velocities. The relationship between distance and recession speed gives the current expansion rate directly. This method anchors itself in the local universe. It also produces a precise number. The two numbers disagree. The disagreement is not within measurement uncertainty. Both measurements have been refined and cross-checked extensively over the past decade. The gap between them has grown more significant with each refinement, not less. The early universe measurement produces a lower expansion rate. The local measurement produces a higher one. The discrepancy is roughly 8 to 9%. In physics, an 8% disagreement between two measurements of the same thing, both conducted carefully and cross-checked independently, means something is wrong somewhere. Either one of the measurements has a systematic error that has not yet been identified, or the Standard Model is missing something that behaves differently in the early versus the late universe. This disagreement is the Hubble tension, and it has been the most acute, unresolved problem in cosmology for nearly a decade. Webb is relevant to the Hubble tension in two ways. First, Webb has been used to independently verify the local distance measurements, specifically checking whether the standard candles used in those measurements, a class of pulsating stars called Cepheid variables, have been correctly calibrated. Early Webb results confirmed the Cepheid calibrations used by previous teams, strengthening the case that the local measurement is correct and the tension is real. Second, Webb's early galaxy findings suggest the early universe was more structured and active than lambda CDM predicts. If the early universe had higher than expected dark matter halo growth, or early dark energy, or modified initial conditions, those same modifications would affect the expansion rate the early universe measurement infers from the cosmic microwave background. Some proposed solutions to the Hubble tension predict specific changes to early universe structure formation that Webb could test directly. The galaxy population Webb observes at high redshift either matches or fails to match those predictions. Webb is therefore not just a passive observer of the tension, but an active tool for resolving it. The Hubble tension and the early galaxy problem are facets of the same deeper issue. The standard model, extremely successful across an enormous range of scales and epochs, is showing cracks at both ends of cosmic time. At the early end, galaxies form too fast. At the late end, the universe expands too fast. Something threading through the entire history of the universe needs revision. That revision may involve physical constants we have always assumed were fixed. Constants that may have been, in the earliest moments of cosmic history, meaningfully different from the values we measure today. Physics rests on a foundation of constants: the speed of light, the strength of gravity, the rate at which atomic nuclei interact, the fine structure constant governing how charged particles and electromagnetic radiation interact. These numbers are measured with extraordinary precision in laboratories and in astrophysical observations. They appear to be the same everywhere we have tested them, across the observable universe and across cosmic time. That universality is a foundational assumption of all physics. Constants are constant. They do not vary in space. They do not change over time. Every equation in cosmology, every simulation, every model of galaxy formation relies on this assumption. What if it is wrong? Several independent theoretical frameworks propose that some constants might have had slightly different values in the extreme conditions of the early universe, not arbitrary variation. Specific, physically motivated changes arising from the interaction of fundamental fields during a high-energy early phase that later settled to their current values as the universe cooled and expanded. The constant most actively discussed in this context is the fine structure constant, which governs the strength of electromagnetic interactions. Some theoretical models predict it was slightly different in the early universe, and astronomical observations of quasar absorption lines have hinted at possible variation at the level of a few parts per million across cosmic time. These hints are not confirmed. They remain tantalizing and contested. More directly relevant to Webb's findings is the effective star formation constant. The rate at which gas converts to stars in a collapsing cloud depends on the interplay of gravity, thermal pressure, magnetic fields, and turbulence. All of these involve physical constants. If any of those constants were slightly different in the early universe, star formation could have been fundamentally more efficient than today, not because of unusual conditions, but because the underlying physics operated differently. This idea is deeply speculative and lacks direct observational support. It is worth mentioning not as a likely explanation, but as an illustration of how far the theoretical investigation has been forced to reach. What is confirmed is that the standard assumption of constant physical constants produces predictions that conflict with Webb's observations. Whether the resolution involves varying constants, modified dark matter, early dark energy, revised initial conditions, or some combination remains entirely open. The scientific process demands that confirmed observations take precedence over theoretical expectations. Webb's observations are confirmed. The theoretical expectations they conflict with are, consequently, in the process of revision. The question is how deep that revision will go. Some researchers argue the answer is not very deep. Moderate adjustments within lambda CDM will suffice. Others argue the answer requires rebuilding from the foundations upward. The implications of that second possibility extend far beyond astronomy. A fundamental revision to our understanding of the universe's origin and structure would reshape physics, philosophy, and every answer we thought we had to the deepest questions about where everything came from. And Webb has already found galaxies that even the revised models cannot explain. Let us be precise about what is and is not at stake. The standard model of cosmology, lambda CDM, is a framework, a highly successful one, built from decades of observations and confirmed by an enormous body of evidence. The findings Webb has produced do not erase that evidence. They add to it. They reveal that the framework, accurate and predictive across a vast range of scales, breaks down or requires significant modification at the extreme early end of cosmic history. If the standard model requires fundamental revision rather than moderate adjustment, the consequences run deep. The most immediate consequence is conceptual. Our understanding of how the universe began and evolved is one of the defining intellectual achievements of the 20th century. It underpins every field that connects to cosmology, particle physics, stellar astrophysics, planetary science, and even, at the farthest reaches, astrobiology. A fundamental revision to the cosmological framework propagates through all of those fields. Specific practical consequences follow. The timeline of heavy element production is central to understanding how quickly rocky planets can form in the universe. If early galaxies ran through stellar generations faster than currently modeled, heavy elements were available in the cosmic medium earlier than we thought. That means rocky planets could have formed earlier in cosmic history, which means complex chemistry, and potentially life, may have had far more time than current models suggest to emerge, not just on Earth, but across the universe. The nature of dark matter, already the most significant known unknown in physics, comes under even greater scrutiny if early galaxies reveal it behaving differently at extreme redshifts. Every proposed dark matter experiment, every detector searching for dark matter particles in underground laboratories operates on assumptions about what dark matter is and how it behaves. Revise those assumptions, and the experimental strategies may need to follow. The Hubble tension, if resolved by a revision to early universe physics, could point toward new particles, new fields, or new interactions that extend beyond the standard model of particle physics. The two standard models, cosmological and particle physics, are deeply intertwined. A crack in one tends to propagate toward the other. Most fundamentally, a confirmed revision to our cosmological origin story forces a confrontation with the question of initial conditions. What set up the Big Bang to produce the universe it produced? If those initial conditions were different from what lambda CDM assumes, why? What physics governs those conditions? And can we ever observe evidence of what, if anything, preceded them? Webb is not answering those questions. It is sharpening them to a point where they can no longer be set aside. And it is doing so by finding specific, confirmed objects that no version of the current framework can explain. The galaxies for which even the revised models produce no satisfactory answer. Most of Webb's impossible galaxies are impossible in the sense that they push the standard model significantly beyond its comfort zone. They require modifications, adjustments, revised parameters. They are, with effort, accommodatable within some version of an updated lambda CDM. A handful are not. Among the thousands of early galaxies Webb has catalogued, a small subset stands apart. They are the cases where the combination of confirmed distance, confirmed mass, confirmed chemical maturity, and confirmed structural complexity stacks high enough that even the most aggressively revised models produce no satisfactory explanation. One category involves galaxies at extreme redshifts with stellar masses, so large that producing them within any lambda CDM variant, however modified, would require conditions that violate other confirmed observational constraints. Every proposed fix for the mass problem encounters a constraint somewhere else in the data that breaks the fix before it can be applied. These are not cases where the data is uncertain. The redshifts are spectroscopically confirmed. The mass estimates, while carrying uncertainties, have been independently cross-checked using multiple methods. The constraints they violate are themselves confirmed by independent observations. Every exit from the problem closes before you reach it. A second category involves the combination of structural maturity and chemical complexity in the same object. Individual galaxies showing extreme chemical enrichment can be explained by invoking unusual stellar populations. Individual galaxies showing unusual structural maturity can be attributed to rare formation pathways. But galaxies showing both simultaneously, at confirmed extreme distances, strain every proposed explanation to breaking point. For these objects, the response from the cosmological community has been honest. Some papers use language like, currently inexplicable within existing frameworks. Others flag them as priority targets for follow-up observations, not because better data will make the problem disappear, but because the better data might reveal a new physical mechanism that could absorb the anomaly. That is the scientific response at its best. Acknowledge what the data says. Acknowledge that no current explanation works. Search for new physics rather than forcing the data into an inadequate model. The honest answer as of the current state of the field, is that a small but significant fraction of Webb's most extreme early galaxy discoveries cannot be explained. They are real, they are confirmed, and they are waiting for a theoretical framework capable of containing them. And Webb is not finished. The telescope has a designed operational lifetime of at least 20 years. It has been in operation for a fraction of that time. The survey programs underway represent a small portion of what the instrument is capable of delivering. The follow-up spectroscopic programs, gathering the precise chemical and kinematic data needed to confirm or revise the most extreme candidates, are still accumulating. Every month, new data arrives. Every month, the picture of the early universe sharpens. Webb is pointing at the edge of everything. Right now, as you listen to this, the telescope is 230 miles per hour in the wrong direction to catch with a spacecraft. Drifting in its gravitational equilibrium point a million miles from Earth, gathering infrared photons that have been traveling for over 13 billion years. Some of those photons left their sources before the Earth existed, before our star existed, before half the stars visible in the night sky were born. The current observational programs include some of the most ambitious deep field surveys ever attempted. One program is accumulating hundreds of hours of exposure time on a small patch of sky, building toward a dataset an order of magnitude deeper than the first Webb deep field images. At those depths, the expectation is to push confirmed galaxy detections to redshifts of 15, 16, possibly higher, corresponding to cosmic times under 250 million years after the Big Bang. Nobody knows exactly what will appear at those distances. The standard model predicts essentially nothing. At redshift 15, the universe was so young that even the accelerated galaxy formation Webb has documented at lower redshifts should not yet have produced detectable objects. The model's predictions, even in their revised forms, fade toward zero at these extreme distances. Webb has a history of finding things where models predicted nothing. A separate program is targeting candidate population 3-star signatures in existing data, pursuing the objects identified as the most likely hosts of first-generation stellar populations. Confirmation of population 3 stars would rank among the most significant astrophysical discoveries ever made. It would close the last direct observational gap in the story of stellar evolution, from the first starlight to the complex stellar chemistry that built the atoms in your cells. Another program is mapping the large-scale structure of the early universe across a wide field, building a three-dimensional picture of how galaxies, dark matter, and cosmic filaments were arranged in the first 2 billion years. This map will either confirm or challenge the clustering predictions that several competing cosmological models make at these early times. It is, in effect, a direct test of the initial conditions of the universe. And Webb is gathering in parallel the spectroscopic data needed to resolve the most extreme galaxy candidates that photometric surveys have flagged over the past 3 years. For each confirmed impossible galaxy that has forced a revision to the theoretical framework, there are dozens of candidates awaiting the precise measurements that will confirm or refine them. The history of this telescope, even in its short operational life, is a history of the universe being stranger than anyone predicted. Every time cosmologists adjusted their expectations and looked again, Webb found something further outside those expectations. The pattern has been consistent enough that the most honest prediction for what comes next is simply this: whatever it is, the models did not see it coming.